Conveying surroundings information of a robot end-effector by adjusting controller button stiffness. Teleoperation tasks involve robots being controlled remotely by humans. They are necessary across numerous domains, including nuclear, underwater, space exploration, telesurgery, industrial, and for safety and rescue operations. Dexterity, the ability to manipulate objects using the hands and fingers to perform a specific task with precision and in a timely manner. The movements must be fully controlled and responsive to the surrounding environment. Otherwise, it can result in damages to the robot itself, the environment, the objects nearby, or even people. It also would not be able to fulfill the task it's commanded to. One reason for the low dexterity in teleoperation is that the teleoperator cannot feel what the robot experiences, nor is in the same environment. When attempting to interact with an object, the robot arm often obstructs the visual information, a phenomenon known as occlusion. Visual information is also insufficient to understand the depth of the object. To enhance the user's awareness of the robot's interaction with the environment, we start with a simulation of the environment in which the robot operates and a model of the surrounding objects. The object's volume is enlarged in the simulation. The intersection volume between end-effector and the virtually enlarged objects is calculated. We use a low-complexity geometrical approach. Based on this value, the stiffness of the controller's buttons are set. Since the method used for input is also employed for haptic feedback, the information is conveyed intuitively and in real time. In this simulation, the intersection volume between the virtually enlarged object and the end-effector increases as it approaches. Both translational and rotational movements are shown. Values for both sides of the end-effector, determining the change in stiffness, are displayed. This helps the user intuitively understand the object's location relative to the robot's gripper. To generate the change of stiffness as haptic feedback, a PS5 DualSense controller is used. With its adaptive triggers, the stiffness is programmable based on the discussed parameters, providing an interaction similar to the one displayed. The system effectively prevents potential contact by alerting the user, allowing for informed decisions during interaction. Through haptic feedback, it provides resistance, resulting in slower and more controlled movements when the gripper is near another object. This also leads to better gripping positions and helps the user understand the target's depth distance. The solution is robust, working well despite differences between real-world conditions and the simulation environment, positional errors, and transmission delays. It prevents collisions and reduces computational complexity by focusing on nearby modeled objects instead of complex meshes.